Good evening, everyone. Myself, I'm Faaiz. I'm from AIIMS Nagpur, and our topic is for today oscillations. Okay, our topic is oscillations. So the first concept is simple harmonic motion. See, okay, when we can call a motion is simple harmonic motion, the condition is yes, we all know that acceleration, directly proportional to minus ex. Right? Yes, this is the condition. Or we can also write A equal to minus omega square x, right? This is the condition for a simple harmonic motion. This is the condition for a simple harmonic motion. Yeah. Next, let's see what are the equations of SHM. Yeah, equations of SHM. See, how do we get equations of SHM? See, the condition is A equal to minus omega square x. We can write A as d square x by dt square, right, plus omega square x is equal to 0. It is a second degree equation, right? Second degree differential. So if we solve this, we will get equations of SHM. What are the equations of SHM? The first one is displacement time relation x is equal to a sine omega t. Second one, if we differentiate, well, we will get velocity. Velocity is a omega cos omega t, and acceleration is minus a omega square sine omega t. Okay, and we know a is equal, any next is acceleration displacement relation a equal to minus omega square x. Next, velocity displacement relation velocity v equal to plus or minus omega into root of a square minus x square, right? Next, time period, we have an equation time period t equal to 2 pi by omega. See here, omega is what? Yeah, angular frequency. Omega is angular frequency. Time period equal to 2 pi by omega, and frequency is 1 by time period. Okay. These equations will be very useful. Okay. Suppose, okay, this is the mean position. Okay, this is the mean position. This is the mean position, and this is x is equal to plus a. Yeah, amplitude. Here x is equal to minus a. So acceleration will be maximum here, right? Why? Because equation of acceleration is minus omega square x. So where x is maximum, acceleration is maximum. So at amplitudes, acceleration will be maximum. At mean position, velocity will be 0, and force F net will be also 0, and acceleration is also 0. Sorry, velocity at mean position will be maximum. Yes, velocity at mean position will be maximum, right? And acceleration and force will be 0 at mean position. Okay, so yeah, we have done equations also. And what is the maximum value of acceleration? A max is minus omega square a. If magnitude a omega square, what is the maximum value of velocity? Is a omega or omega into. Okay, so let's see the first question. This is the first question. When a particle executes simple harmonic motion, the nature of graphical representation of velocity as a function of displacement. Okay, simple. We know the equation. We have to graphically represent velocity as a function of displacement. So what is the equation relating velocity and displacement? Yes, velocity equal to, you have studied already, velocity v equal to omega into root of a square minus x square. So what I am doing is I'm taking v by omega equal to root of a square minus x square, square both side, v square by omega square equal to a square minus x square. So we got an equation like x square plus v square by omega square equal to a square. This is the equation of what? Ellipse, right? So the graph will be elliptical in shape. So our answer will be option 1, elliptical. Okay. Moving on to next question. Xt graph of a particle undergoing simple harmonic motion is shown below. So we got xt graph, position, displacement, and time graph. The acceleration of the particle at time period is given time 4 by 3 seconds. Okay. Okay, this is the graph, right? This is the graph. This is the graph. So from main position to reach here, this will be one time period, right? So in question it is given time period is how much? 8. Okay, time period is how much? 8. Okay, so time period will be 8. So if time period is 8, omega will be 2 pi by 8, that is pi by 4. So we got omega, pi by 4. Okay. We have to find out acceleration. For that, we have to know what is amplitude, right? What is the formula of acceleration relating with the time? Minus a omega square sine omega t. So let me write that. Yeah. The formula is acceleration equal to minus a omega square sine of omega t. We have to find out amplitude. Okay, amplitude is what? Amplitude is also given in question. Okay, this is the amplitude. Amplitude is 1 centimeter. Amplitude is 1 centimeter. So I'm just applying those values. Acceleration equal to minus 1. Okay. I'm not converting into meter because options are also in centimeter. So 1 into omega square, pi square divided by 16. Sine of omega is pi by 4. Time period, we have to find out time at 4 by 3. So time t is 4 by 3 into 4 by 3. Right. We can cut 4. So it is coming as acceleration A equal to minus pi square by 16 sine of pi by 3. What is sine pi by 3? What is sine 60? Sine 60 is root 3 by 2. Acceleration will be minus pi square by 16 into root 3 by 2 or root 3 pi square divided by 32 is minus root 3 pi square by 32 centimeter per second square. So which option is correct? Option D will be the correct answer. Yes, let's move on to next question. A particle performs simple harmonic motion with amplitude A. Amplitude is A. Okay. Its speed is troubled. Yeah, speed become 3v. If the initial speed is v, speed become 3v at the instant that it is at a distance 2a by 3 from equilibrium position. Okay. Let me picturize first what is given in the question. Okay. So the scenario is like this. Okay, this is main position. This is amplitude. Okay, plus a minus a. Okay. When the particle is at a distance 2a by 3, 2a by 3 from the equilibrium position, almost here. Okay, at 2a by 3, initial speed was how much? Is initial speed is v only. But what they did at 2a by 3, speed is troubled. Yes. Okay, the particle reached at 2a by 3 with velocity v. After that, they troubled the velocity. So final velocity become 3v at 2a by 3. So now, the amplitude of SHM will change. I have to find out that amplitude, that new amplitude, a dash. We have to find out that. For that, we know velocity displacement relation. Velocity v equal to omega into root of a square minus x square, right? We can apply here how. So in first case, velocity v initially is v only. omega into root of amplitude is a only. Okay, a square minus x is 2a by 3. 2a by 3 square, 4a square by 3. No, 4a square by 9. 4a square by 9 divided, okay, over. Next is velocity troubled 3v, which is equal to omega into root of. So now new amplitude, write a dash square minus minus 2 x is 2a by 3 only, again 4a square by 9. Okay, let me just divide these equations. Means, yeah, equation 2 by 1, that is 3v divided by v. So 3 will be equal to omega omega I can cut, v I can cut. 3 will be equal to root. So root I'm taking square root. So 3 square will be equal to a dash square minus 4a square by 9 divided by a square minus 4a square by 9. Okay, just solve this. You will get the equation. 9 will be 9a dash square minus 4a square divided by 9. 9 into divided by 9a square by 4 by 9. Okay, so into 9 divided by 9a square minus 4a square. 9 we can cut. So I'm taking 9 this side. How much? 81a square minus a. Okay, 9a square minus 4a square. How I can write 5a square, right? So this will be 5a square. 9 into 5. 45a square equal to 9a dash square minus 4a square, or 9a dash square equal to 49a square. Okay, a dash square equal to 49 by 9a square. Okay, or a dash equal to 7 by 3a. Right, 7 by 3a is the correct answer. Which option? Yeah, 7a by 3. 7a by 3 is the correct option. Right. Let's see next. What is initial phase? Initial phase in the sense, if C, if at time period t equal to 0, if I am at equilibrium, then there is no need of initial phase. Suppose, what if at time period t equal to 0, yes, particle is starting SHM at time period equal to 0, but not at equilibrium position at x is equal to amplitude. So there will be a phase difference, right? How can we solve that? We know that x is equal to a sin omega t. So when time period equal to 0, its displacement is a. So a equal to a into sin 0. Sin 0 is no. Wait. So if this is starting, it will have a phase, right? Why? Because it is not starting from equilibrium. A sin phi. So sin phi will be 1. That means here phi will be 5. That is a concept of initial phase. So when the particle is starting SHM at x is equal to a, okay, then initial phase is pi by 2. Okay. So by just modifying the equation, x is equal to, we can write a sin omega t plus phi, velocity a omega cos omega t plus phi, acceleration minus a omega square sin of omega t plus phi. Okay, just modifying those equations. Okay. So let's solve question. This is the first question. Y equal to a into sin of omega t plus phi 0 is a time displacement equation of SHM. At time t equal to 0, the displacement of the particle is y equal to a by 2 and it is moving along negative x direction. Then the initial phase phi 0 will be. It's a little bit tricky question still. Okay, let's solve this. So the equation is y equal to a of sine omega t plus phi c. And it is given at time period t equal to 0, displacement of the particle is a by 2. So a by 2 equal to a sine time period t equal to 0. So phi 0. That means sine phi 0 equal to 1 by 2. That means phi 0 equal to sine inverse of 1 by 2 pi by 6. Right? Pi by 6. Okay. But see, this is not the initial phase. Why? Let me draw. See, this is the main position. The particle is oscillating like this, and like this. Okay. And it is given that, okay, so now particle is at a by 2. Okay, this is a by 2. This is a, this is minus a. Okay. Now particle is at a by 2 and it is moving along negative x direction. Anyway, negative y direction, okay, it doesn't matter, right? So it is moving negative, okay, negative direction. So the particle is first to reach here, it is moving, yeah, this direction. Moving this direction. Moving this direction means the velocity will be negative. Why? Here velocity is positive, right? This side velocity will be negative. So what is equation of velocity? A omega cos of omega t plus phi 0. Right. So I put velocity equal to a omega cos of pi by 6. So cos pi by 6 will be root 3 by 2. But the velocity is positive, right? So velocity should be negative. Velocity should be negative. So which quadrant? Cos pi by 6? Yes. Just do pi minus pi by 6. It will be second quadrant, right? Pi minus pi by 6. So our answer will be 5 pi by 6. Our answer will be 5 pi by 6. This is our answer. Okay. This is the next question. The ratio of maximum acceleration to maximum velocity in a simple harmonic motion is given. At time period t equal to 0, the displacement is given. What is the maximum acceleration? You have to find out maximum acceleration. It is given initial phase is pi by 4. Let's do this. We have A max by V max relation. What is the equation of A max? A omega square. V max, A omega. So this is actually omega. So we have omega here, 10. 10 rad per second. Okay, unit is rad per second. Next, at time period t equal to 0, displacement is 5 meter. At time period t equal to 0, displacement is 5 meter. That means displacement 5 equal to A sine time period t equal to 0. So omega t will be 0 and initial phase is pi by 4. So it will be 5 equal to A into sine pi by 4. So 1 by root 2, A equal to 5 root 2 meter. Right, so we got A, we got omega. We have to find out maximum acceleration. So maximum acceleration is A into omega square. A is how much? 5 into root 2. So 5 into root 2 into 10 square. That is 100 into 5 root 2. That is 500 root 2 meter per second square. 500 root 2. Which option? Yeah, option B will be the correct answer. Okay, yes. Okay. We have one more question. A particle executes SHM of a amplitude A along x-axis at time t equal to 0. The position of the particle is x is equal to A by 2, and it moves along positive x-axis. The displacement of the particle in time t equal to okay. We have to find out initial phase. Okay, just Okay, simple question. We have to find out initial phase. So it is given time period t equal to 0. Particle is at a by 2. A by 2 will be a into sine delta omega t will be 0, right? So how much sine delta will be 1 by 2. That means delta will be pi by 6. But it is here there is no complication because it is given it is moving along positive x-axis. It is moving along positive x-axis. So velocity will be also positive. So just we can put answer. Option 2 is will be the correct answer. Option 2 will be the correct answer. Okay. Next, let's see spring block system. A very interesting list. Spring block system. Let me draw the diagram. It's everyone's favorite spring block system. We have a mass of block M and spring of spring constant K. So what if I displace the block M this direction X? So force will be towards this direction, right? It will be minus Kx. Okay, so force is minus Kx. Force is minus Kx. So we know in spring block system, force will be minus Kx. So we can write MA is minus Kx. Or we can write A equal to minus K by Mx. So CC. So condition of SHM is A will be proportional to minus X. So it is A equal to minus K by Mx. So spring block system will do SHM. So it will have a time period and we know A equal to minus omega square X. So from this we will get omega will be root of K by M. First equation. We know time period T equal to 2 pi by omega. So time period T will be 2 pi into root of M by K. Time period T equal to 2 pi into root of M by K and angular frequency is root of K by M. Easy, very easy. Okay. Next, let's see combination of springs. In combination of spring also just simple concept only. So okay, we have two case. This is the first case. Two spring having KK. This is the mass M. Okay, this is the first case. And in second case, M spring constant KK. So the equation will be T will be 2 pi into root of M by K. Here T will be 2 pi into root of M by K effective or K equivalent, right? For parallel condition, for parallel connection, K effective will be like capacitor K1 plus K2. And for series connections, series spring connection, K effective will be 1 by K effective will be like 1 by K effective will be 1 by K1 plus 1 by K2. Right. So here how much will be the effective? This is parallel connection. So 2K. Here how much? Like here will be for K1 plus K2 divided by K1 K2. 2K by K square. 2K by 2K by K square. Okay. Yes. So here will be K1 K2 by K1 plus K2, K square by 2K, K by 2. Simple this combination of springs. Let's solve first question. The given figure, a mass capital M is attached to a horizontal spring which is fixed on one side to a rigid support. The spring constant of the spring is K. It's given. The mass oscillates on a frictionless surface with a time period T and amplitude A. Okay. Now what happens? Now, when the mass is in equilibrium position, as shown in figure, another mass small m is generally fixed upon it. The new amplitude of oscillation will be. At first condition means when the capital block only at equilibrium. There is no small m at first condition, right? At first situation. So at first situation, capital M block is here and K is here. Okay. So at equilibrium, at x is equal to 0, this block is having a velocity a omega. Now is also when the small m is generally fixed upon it at equilibrium. Okay, this system having a velocity, right? That is v dash will be equal to a dash omega dash, right? Amplitude also changes and angular frequency also changes. So velocity changes. So by here is there is no net external force. By conserving the momentum, by conserving momentum, by conserving momentum. Yes, initial momentum will be equal to final momentum. Initial momentum is capital M into velocity is a omega equal to final momentum is final mass into yes final velocity a dash omega dash, right? And we know omega is omega. What is the formula for omega? Omega is root of k by m. So m a root k by m equal to m plus m into a dash. We don't know, right? You have to find out a dash, new amplitude. A dash omega dash will be root of k divided by m plus m. Okay. So let's solve this. So okay, this is capital M. So root m, okay, 1m we can cancel there. So we will get root capital M a root k we can cancel equal to root of m plus m into a dash. So a dash will be a into root of m divided by m plus m. Capital M divided by capital M plus small m. A into root of capital M by yes. So option A looks like the correct option, right? Yes, that is the correct option. Let's see, we have another question here from spring block system. A block of mass 2 kg is attached with two identical springs of spring constant 20 Newton per meter each. Okay, spring constant is given, mass of the block is given. The block is placed on a frictionless surface and the ends of the spring are attached to rigid supports. When the mass is displaced from its equilibrium position, execute simple harmonic motion. Okay, time period of oscillation is given, the value of x. Oh, it's very simple, right? Yes, here is two spring, right? If suppose its spring constant is k, its spring constant is k. See, which kind of combination is this? This is parallel combination, right? This is parallel combination. For parallel combination, K effective will be K1 plus K2. So here K effective will be 2K because same spring constant, two identical springs. So let's solve. We know the time period equation, time period T equal to 2 pi into root of M by E. K effective, okay. So it's given question time period of oscillation is pi by root x. Just equate with this pi by root x. Okay, so let's cut pi and I'm squaring both the side. 4m divided by k effective is 2k, which is equal to 1 by x. So we have x is equal to k divided by 2m. Okay, k is given 20, mass is 2, 20 by 4, that is 5. Our answer is 5. Our answer is 5. Okay, x is 5. So yeah, next let's see energy in SHM. Energy. Energy also very simple. When the block is at equilibrium position, it will have only kinetic energy, because see, total energy is half mv square plus half kx square. Right, right. Okay. And what is the equation of velocity? Yeah, omega into root of a square minus x square. So half in m into omega square a square minus x square. Right. Plus half into k, we can write omega is root of k by m. That is k equal to m omega square. So half into m omega square x square. So this is the equation of total energy in a SHM. Okay. See, solve this, 1 half omega square x will get cancelled. Total energy is actually how much? Half ka square. That is constant. So in SHM, total energy is constant. See, this is the graph, parabolic graph. For kinetic energy, it's upward parabola, and for potential energies, see, downward parabola for kinetic energy. Okay, so at C, at maximum, at amplitude, this is the main position. At amplitude, kinetic energy will be 0, and potential energy will be maximum. And at equilibrium, kinetic energy will be maximum, potential energy will be 0. Right? Yes. Let's solve first question. For what value of displacement, kinetic energy and potential energy of a simple harmonic motion will become equal? Easy. For what value of displacement, kinetic energy and potential energy of simple harmonic motion equal? So it's given potential energy equal to kinetic energy. What is potential energy? Half kx square. K we can write half m omega square x square equal to kinetic energy. What is half m omega square a square minus x square? Right. Okay, I'm cutting half omega square, half omega square. So x square will be equal to a square minus x square. So a square equal to 2x square. So x will be a divided by root 2 plus or minus. Right, both sides. So our option 3 will be the correct answer. Okay. Yes. This next question. A particle is executing simple harmonic motion with a time period t. At time t equal to 0, it is at its position of equilibrium. The kinetic energy time graph of the particle will look like. Simple. See, what is the equation of kinetic energy? Kinetic energy equation is half m omega square into a square minus x. So this is first equation. And we have half m into v square, right? What is v? V is a omega cos omega t, right? See, we've already seen that. Velocity, where is velocity? Is a omega cos omega t. We have that equation also. But here, see, here we know that kinetic energy will be 0, where kinetic energy will be 0, where kinetic energy equal to zero when it is at amplitude, right? To which time period amplitude will attain? So at amplitude time, kinetic energy will be zero. So we have to find out x is equal to a sin omega t from this equation. At which time displacement will become amplitude? So a equal to a sin omega t, because at amplitude a, kinetic energy will be zero. We know that. So sin omega t will be 1, that is pi by 2, right? So omega t will be pi by 2. Omega t will be pi by 2, right? So omega time period t will be pi by 2 by omega. Pi omega means 2 pi by t. That is t by 2 pi. That is at time period t equal to pi by 4, the particle attains amplitude. See, for simple, we can say like this. Actually, yes. From t equal to 0, here t by 4. Okay. So particle reaches at amplitude in time t by 4, then again reaches here at t by 2, reaches here 3t by 4, again reaches here time by t. So at t by 4, kinetic energy will be 0. In which option at t by 4 kinetic energy is 0? Only B option. Option B, see, at t by 4 kinetic energy is 0. Option B will be the correct answer. Okay, this is next question. A particle undergoing simple harmonic motion has time-dependent displacement given by x is equal to a sine pi t by 90. The ratio of kinetic energy to potential energy of this particle. Okay. Before that, okay, you have to find out a ratio of. You have to find out what? You have to find out ratio of kinetic energy divided by potential energy, right? We can write kinetic energy as total energy minus potential energy, right? So we will get total energy by potential energy minus 1. So we have an equation. What is total energy? Half k a square. It's always constant. What is kinetic energy? What is potential energy? Half k x square minus 1. Right. So half k get cancelled. So a square by x square minus 1. This will be our answer, right? So we have to find out x. You have to find out what is x. For that, our equation is x is equal to a sine of pi by 90. Time period is 210. 210. 7. Okay. So we have to find out sine 7 pi by 3. Sine. Okay, we can write 7 pi by 3 as 2 pi plus pi by 3. So at positive quadrant, right? So it will be equal to sine 7 pi by 3 will be equal to sine pi by 3. What is sine pi by 3? Root 3 by 2. So x is equal to a in root 3 by 2. That is root 3a by 2 will be the displacement. So to this equation, just apply a square by root 3a by 2 whole square means 3a square by 4 minus 1. This will be how much? 4a square by 3a square minus 1. That is a square by 3a square. That is 1 by 3. Or 1 is to 3. 1 by 3. Okay. Ratio is 1 by 3. Okay. Let's solve the next question. Which graph represents the difference between total energy and potential energy of a particle executing SHM versus its distance from mean position? So we know that potential energy, total energy is always constant. Potential energy at equilibrium will be 0. This option is wrong. This option is also wrong. Right, this is the graph of potential energy. This is the graph of potential energy. At equilibrium, potential energy should be zero. So both one option, two option cancelled. This is not the, so option 3 will be the correct answer. Right, yes. Next question. The amplitude of a particle executing SHM. The amplitude of a particle executing SHM is 3 centimeter. And the displacement at which its kinetic energy will be 25% more than the potential energy is. So it is given that kinetic energy is will be 25% more than the potential energy. That is potential energy plus which kinetic energy is will be 25% more than the potential energy, right? K by 4. No. P by 4 only, right? Yeah. P by 4, right? Kinetic energy is to displacement of kinetic energy will be 25% more than the potential energy. P plus P by 4. So kinetic energy is 5 by 4 potential energy. Just apply those values. Kinetic energy is 1 by 2 m omega square a square minus x square is equal to 5 by 4 1 by m omega square x square, right? So 4a square minus 4x square will be 5x square. 4a square will be equal to 9x square, or 2a equal to 3x, or x is equal to 2a by 3. A is given 3. So 6 by 3, that is 2 centimeter. Our answer will be 2 centimeter. Our answer will be 2 centimeter. Next, a particle is executing simple harmonic motion. The ratio of potential energy and kinetic energy of the particle when the displacement is half of its amplitude. We have already solved that ratio of potential energy and kinetic energy. Again, see ratio of potential energy to kinetic energy. Potential energy to kinetic energy. Yes, we can write potential energy as total energy minus kinetic energy divided by kinetic energy. This will be total energy divided by kinetic energy minus 1, right? So half m no half ka square divided by half m omega square a square divided by half m omega square a square minus x square minus 1. So this we can cut. It is given that displacement is a by 2. So this will be a square divided by a square minus a square by 4 minus 1. That is a square divided by 3a square 4 minus 1, or a square divided by 3a square, or 1 by 3, or 1 is to 3. So which option? 1 is to 3. Option 2 is the correct answer. 1 is to 3. This next question. An object of mass m is suspended at the end of a massless wire of length L and area cross section A. Right, young modulus of the material of the wire is y. And if the mass is pulled down slightly, its frequency of oscillation along the vertical direction is simple, right? This is the condition. I have a massless wire, right? wire is here of length L. Okay, mass M is here, is displaced. Okay, if I displace X downward, we know that Young's modulus, right? Young's modulus is F A, F by A, or F by A divided by. So here delta L is X. So from this we can write AY divided by L into delta L will be F. So see, we got right, F is equal to something constant into X. So the constant K here is AY by L. And we know time period T equal to 2 pi into root of M by K. But they ask, so frequency will be 1 by 2 pi into K here is AY. So ML. So option AY by ML, option B seems to be the correct answer. Simple question, right? Next is our angular SHM, that is pendulum. Yes. Here the concept is net torque directly proportional to theta, and net torque will be equal to some constant K into theta, and time period equal to 2 pi into root of I by K. Right. From this time period, we can derive a simple pendulum time period T equal to 2 pi into root of L by G. Right? Yes. So we have first question here. This is the question. The mass and the diameter of a planet are 3 times the respective values of for the Earth. The period of oscillation of a simple pendulum on the Earth is 2 seconds. The period of oscillation in the same pendulum. Okay. Just just playing with the G effective, right? 2 pi into root of L by G effective. So it's given in the question. Radius, diameter, okay, again, radius, same ratio. So radius of planet we can write the 3 into radius of Earth, and mass of planet is 3 into mass of Earth. Right. So GP will be GMP divided by RP square. So we can write G into 9 weight, G into 3ME divided by 9RE square. So 3 we can cut. This will be G by 3. GP will be GE by 3. Right, GE by 3 or G by 3. Right. So we know what is the equation of time period. T P will be 2 pi into root of L by G effective L by G by 3, or root 3 into time period of Earth. So time period of planet will be root 3 into time period in the Earth is 2 seconds. So 2 root 3 second will be the correct answer. Very simple question, right? Yeah. So option D will be the correct answer. 2 into root 3. This is next question. Choose the current length L versus square of time. Graph of a simple pendulum executing simple harmonic motion. Again, very simple question. Time period T equal to root of 2 pi into root of L by G. So we know that time T square equal to 4 pi square L by G. That means T square proportional to length. T square is proportional to length. Which option? Option 3 will be the correct answer. Okay. Next, let's see what is damped oscillation. Damped oscillation, the displacement equation is x is equal to a0 and e raised to minus bt by 2m sine of omega dash t plus delta. Let's forget about that. Just remember this equation. Amplitude will change in damped oscillation, right? Damped oscillation will be like this only. Like. So amplitude will change with respect to time. The equation of amplitude is with respect to time a equal to a0 into e raised to minus bt divided by 2m. This is the equation. We have a question here, previous year question. Amplitude of mass spring system which is executing simple harmonic motion decreases with the time. Okay, of course we know that because that is damped oscillation. Here B is what? Here B is decay constant or drag constant. Okay. That is given in this question. How much time is required for the amplitude of the system to drop to half of its initial value? So amplitude, yeah, what time amplitude will become a0 by 2. So just to see again playing with those equations, a is a0 by 2 here, a0 into e raised to minus bt by 2m. So 1 by 2 will be 1 by 2 will be 1 by 2 a e raised to minus bt by 2. So I'm taking ln both side, ln 2 will be, okay, minus minus will get cancelled, 1 by 2, right? So ln 2 will be how much? Ln bt by 2m. So bt will be 2m ln 2, or time period t equal to 2 into m into ln 2 divided by b. We have all values, right? What is m here? Gram get cancelled, so don't worry about that. 2 into 500. Ln 2 is given 0.6 and I'm taking 0.7. B is 20. That is gram per second. So gram will cancel each other. So to 50 into 0.7. That is 35. So 3.5. 35 only. 50 into 0.7, right? So this will be 35. 35 second. Oh yeah, option 1, 34.6. Approx is 35, no? Yeah, that will be the correct answer. Yeah. Here we have the last question. Again, from damped oscillation, the displacement of a damped harmonic oscillator is given by x is equal to e raised to, this is given, e raised to minus 0.1 t cos, okay, 10 pi t plus 5. Here it is in second. The time taken for its amplitude of vibration to drop to half of its initial value is close to. So at present, the amplitude is c. By comparing with this equation, see, this is the amplitude wala equation. This is amplitude equation, right? By comparing with that equation, now we have amplitude equal to e raised to minus 0.1. So it's given that half of the initial, so 1 by 2 will be e raised to minus 0.1 t. Alright, so ln 2 will be 0.1 t. E will be 10 into ln 2. ln 2 is 0.7, that is 7 second. So option B will be the correct answer, 7 second. Okay, yeah. So we covered almost everything. And we solved 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yeah, you almost covered 19 questions in 1 hour, okay? Yes, good. That is good actually. So